Black holes stand as enigmatic sentinels scattered throughout the vast cosmic ocean. These celestial objects possess a gravitational pull so intense that nothing, not even light, can escape their grasp. They are regions where the very fabric of space-time is warped beyond recognition, challenging our understanding of the universe. Imagine a place where the laws of physics as we know them break down, a place of infinite density and zero volume. This is the captivating allure of black holes. Black holes are not merely cosmic vacuum cleaners, relentlessly devouring everything in their path, as often depicted in science fiction. Instead, they are fascinating objects of extreme gravity, shaping the cosmos around them. They influence the evolution of galaxies, ignite star formation, and hold clues to the fundamental nature of gravity itself. Their existence, once a controversial prediction of Einstein's general theory of relativity, is now widely accepted within the scientific community. Their story intertwines with the life cycles of stars, the evolution of galaxies, and the very essence of space and time. Join us as we journey into the heart of these cosmic enigmas, exploring their formation, properties, and the profound influence they exert on the universe we inhabit. Black holes, despite their mysterious nature, are not cosmic oddities but rather the end product of a star's life cycle. To understand their formation, we must first delve into the heart of a dying star. Stars, like our Sun, are immense balls of hot, glowing gas, powered by nuclear fusion in their cores. This fusion process creates outward pressure that counteracts the inward pull of the star's own gravity. For much of a star's life, these forces remain in equilibrium, allowing it to shine brightly for billions of years. However, this balance cannot last forever. As a star exhausts its nuclear fuel, the outward pressure from fusion weakens. Gravity, relentless and unforgiving, begins to dominate. The star's core contracts under its own weight, becoming denser and hotter. For massive stars, those at least 8 times the mass of our Sun, this collapse triggers a cataclysmic explosion known as a supernova. This explosion, visible across vast cosmic distances, briefly outshines entire galaxies. In the aftermath of this stellar demise, the core remains, crushed by gravity into an infinitesimally small point known as a singularity. A black hole is born. The universe, in its vastness, harbors a variety of black holes, each distinguished by its mass and origin. Astronomers categorize these enigmatic objects into 3 primary types: stellar mass black holes, supermassive black holes, and intermediate mass black holes. Stellar mass black holes, as their name suggests, form from the collapse of massive stars. These black holes, typically 3 to 10 times the mass of our Sun, are scattered throughout galaxies, remnants of stellar evolution. Supermassive black holes, on the other hand, reside at the centers of galaxies, including our own Milky Way. These gravitational behemoths, millions or even billions of times the mass of our Sun, exert a profound influence on their galactic neighborhoods. Their origin remains a topic of active research, but their existence is undeniable. Intermediate mass black holes, as their name implies, bridge the gap between stellar mass and supermassive black holes. These objects, hundreds to thousands of times the mass of our Sun, are thought to form through the merger of smaller black holes or the runaway collapse of massive stars in dense stellar clusters. These different types of black holes, though diverse in their properties, share a fundamental characteristic: an event horizon. Imagine approaching a black hole, drawn in by its immense gravitational pull. As you get closer, you would notice that the black hole's gravity warps the fabric of space-time, causing light to bend around it. This bending of light creates a strange visual effect, distorting the background stars and making them appear as smeared arcs. As you venture closer still, you would eventually reach a point of no return, a boundary in space-time known as the event horizon. The event horizon marks the point where gravity's pull becomes so strong that nothing, not even light, can escape. Once you cross this invisible threshold, you are forever trapped within the black hole's grasp. The event horizon is not a physical boundary, but rather a mathematical concept. It represents the point where the escape velocity from the black hole's gravity exceeds the speed of light. As you fall towards the black hole's singularity, time itself begins to slow down for you relative to an outside observer. This phenomenon, known as time dilation, is a consequence of Einstein's theory of general relativity. Time's distortion, gravity's relentless grip. Imagine 2 identical clocks, one placed near a black hole and the other far away in a region of weak gravity. As you observe these clocks from a safe distance, you would notice something peculiar. The clock near the black hole appears to tick more slowly than the clock far away. This difference in timekeeping, known as gravitational time dilation, is a direct consequence of the intense gravity near a black hole. Einstein's theory of general relativity tells us that gravity warps spacetime, and this warping affects the flow of time. The stronger the gravity, the slower time flows. Near a black hole where gravity is extreme, this effect becomes particularly pronounced. If you were to fall into a black hole, time would continue to slow down for you relative to an outside observer. However, from your perspective, time would appear to flow normally. You would not notice any difference in your perception of time. However, to an outside observer, you would appear to slow down as you approach the event horizon, eventually freezing in time at the very edge. The Singularity, a mystery shrouded in darkness. At the heart of a black hole lies a point of infinite density and zero volume known as the Singularity. This point represents the ultimate demise of matter as it is crushed by the relentless force of gravity. The Singularity is often described as a point of no return, where the laws of physics as we know them break down. Our current understanding of physics cannot fully describe what happens at the Singularity. The curvature of spacetime becomes infinite, and the very concept of space and time loses all meaning. Some theories suggest that the Singularity might be a gateway to other universes or dimensions, while others propose that it represents the ultimate end of everything. The Singularity remains one of the most profound mysteries in modern physics, a puzzle that continues to intrigue and challenge scientists. While we may never be able to directly observe the Singularity, its influence on the surrounding spacetime is undeniable, shaping the evolution of galaxies and the fabric of the cosmos. Bridges through spacetime, wormholes, and black holes. Imagine a shortcut through the vast expanse of spacetime, a cosmic tunnel connecting distant regions of the universe. This is the tantalizing concept of a wormhole, a theoretical object that has captured the imaginations of scientists and science fiction writers alike. Wormholes, like black holes, are predicted by Einstein's theory of general relativity. They are essentially shortcuts through spacetime, connecting two distant points through a tunnel-like structure. While there is no direct observational evidence for the existence of wormholes, they remain a fascinating area of theoretical research. Some theories suggest that wormholes might be connected to black holes, with the Singularity at the center of a black hole serving as one end of the wormhole. However, the extreme gravitational forces near a black hole would likely make it impossible to traverse a wormhole, even if one were to exist. Unmasking the invisible, studying black holes. Despite their elusive nature, black holes are not invisible to our telescopes. While we cannot directly observe the Singularity or the region within the event horizon, we can study black holes through their effects on surrounding matter. One way astronomers detect black holes is by observing the behavior of stars orbiting around them. These stars, caught in the black hole's gravitational grip, move at incredibly high speeds, revealing the presence of an unseen, massive object. Another method involves studying the radiation emitted by matter falling into a black hole. As gas and dust spiral inward towards the event horizon, they heat up to extremely high temperatures, emitting X-rays and other forms of radiation. By observing this radiation, astronomers can infer the properties of the black hole, such as its mass and spin. In 2019, the Event Horizon Telescope, a global network of radio telescopes, captured the first ever image of a black hole, providing direct visual evidence for their existence. This groundbreaking achievement marked a major milestone in our understanding of these enigmatic objects. Black holes, once considered theoretical curiosities, have now taken center stage in our exploration of the cosmos. As we continue to probe their mysteries, we gain a deeper understanding of the universe's most extreme environments and the fundamental laws of physics that govern them.